Good evening. And thank you for tuning in, joining us for this live streamed astronomy presentation, Neutrinos, the Ghosts from Space, with Jonah Miller. I am Galen Gisler with the Pajarito Environmental Education Center, or PEEC, located in Los Alamos, New Mexico. I will be the moderator for tonight's talk. PEEC has lots of ways you can interact and connect with nature even while we're closed. Check our website, peeknature.org. All our online content, including outdoor challenges and talks like this one, will be there. We'll send you an evaluation form after the talk, and we'll use your comments to improve future programs. We are able to offer programming at this time because of our wonderful members and donors, so we'd like to thank you for your continuing support. Our presenter, Jonah, will be taking questions via Zoom chat. To find the chat feature, look for the Zoom app menu bar. You might have to move your mouse for it to show up. You'll either see a chat icon in the menu bar, or you might need to click more in the menu bar to find the chat option. Type your questions for Jonah into the chat window anytime during the show, and I will relay the questions to him. Jonah Miller got his PhD at the Perimeter Institute for Theoretical Physics. He's now an astrophysicist at Los Alamos National Laboratory. His research focuses on using big computers to model black holes, neutron stars, and supernovae. Recently, he spent a lot of time looking at the critical role neutrinos play in neutron star mergers. I'll turn it over to Jonah now and monitor for any questions or comments coming in on the chat. Enjoy. Go ahead, Jonah.
Hi, everyone. Thanks for joining us. So this story starts, as most good stories do, with radioactive decay. And about 100 years ago, these are some of the folks who came up with and discovered radioactive decay. You might recognize the name Marie Curie. So the picture on the right, these are the Curies, Mary and her husband Pierre, who worked together in their laboratory. And on the left, this guy is Henry Becquerel. And what they discovered was that some atoms, in the parlance at the time, seemed to have their own energy source. And it turned out they were throwing off stuff. They characterized this stuff by blocking it with other stuff. So they discovered that there was one type of thing emitted by atoms, some kinds of atoms anyway, that they called alpha particles, which was, you could stop it basically with just a sheet of paper or some aluminum foil. Beta particles, they discovered, could be stopped not by a single sheet of aluminum foil, but a couple sheets. Now, we now know there's a third type, which is called gamma radiation, which goes through aluminum and all sorts of other stuff, like lead. And just to remind you, what we now know an atom is, although they didn't know this at the time, is there's, in the center of it, some things we now call protons and neutrons, which live in something called the nucleus. And orbiting, and I say orbiting in quotes, because this isn't really what's going on, but it's good enough for what we're talking about tonight. Orbiting the nucleus are electrons. So protons are positively charged, electrons are negatively charged, and neutrons don't have any charge. And what's happening when radioactive decay happens is the nucleus is changing. So a uranium atom, when it emits an alpha particle, for example, changes into a thorium atom. The number of protons and neutrons in the nucleus, which determines the element, what kind of material it is, gold or silver or air or oxygen, which is an air, it changes from one element to another. So uranium might change into thorium under alpha decay. Carbon might change into nitrogen under beta decay. So you may remember hearing about ancient alchemists looking for the philosopher's stone, which can transmute anything into gold, lead into gold, for example. And it turns out there's no philosopher's stone, but the transmutation of one material into another is real. It happens not through alchemy, but through nuclear decay and through nuclear fusion or fission, which are different kinds of nuclear reactions that can happen to an atom under the right conditions. So what's going on with beta decay? In beta decay, I told you that nitrogen or carbon turns into nitrogen. What's really going on? Well, an atomic nucleus, not the whole atom, the nucleus itself is emitting an electron. That's what a beta particle actually is. And what's really going on here is that this neutron, the neutral particle, splits into a proton and an electron, one with positive charge, one with negative charge, and the electron flies off. And so you get more protons and one fewer neutron than you had before the beta decay. And one thing I want to highlight here is this guy. This is the star of our story, the electron neutrino. It turns out there's actually 3 kinds of neutrinos, 6 really. I'll tell you why in a minute. The electron neutrino, the muon neutrino, and the tau neutrino. Each of these is coupled to a different kind of subatomic particle. I told you about the 3 main particles in an atom, protons, neutrons, and electrons. It turns out there's a lot of other stuff down there. We're not really going to talk about it, but there are these things called muons and these things called tauons, or tau particles. And of course, you know about electrons. And so for each one of these kinds of particles, there's a neutrino associated with it. But there's actually 3 more neutrinos, which are the antineutrinos. You might have heard that there's matter and antimatter, and when they touch, they annihilate each other. Well, that's true for neutrinos too. There's neutrinos and there's antineutrinos. So an electron neutrino has an electron antineutrino. Muons have muon antineutrinos, and tau particles have tau antineutrinos. And I told you before, I showed you this categorization of radiation coming from a radioactive atom. But neutrinos, they're in a whole nother level. Neutrinos pass through everything. There's neutrinos passing through the entire Earth every second. And they're everywhere. They've passed through you. Billions and billions of neutrinos are passing through you every second. This is why it was called them ghosts. They phase through everything. And these pictures are what happens if you take a cloud of gas and wait and look very carefully. This is called a bubble chamber. And I'm showing one on the left that was used in CERN, where now the LHC is, and one on the right in Fermilab in Chicago. And all those lines are subatomic particles that you can't see by the naked eye that are passing through you every minute, that you can see when they pass through a cloud of gas and they leave a trail behind. And a lot of those are neutrinos, and many more neutrinos pass through and don't even leave a trail. And neutrinos are produced in the atmosphere. Every moment of every day, particles from space hit stuff in the atmosphere high above us and produce a ton of neutrinos. And lots of those neutrinos pass through you, pass through the Earth. They go everywhere. And one thing that's cool about things that go through other things, like neutrinos, is they're kind of like X-rays, right? So an X-ray machine lets us look through our bodies and see what's inside, like our skeleton. And that's because X-rays, which are a kind of light, pass through our bodies. Well, the same story kind of holds for neutrinos. Well, they pass through our bodies, but they also pass through things in space, like the sun. And that means they're kind of like X-rays for space stuff, like the sun. So the sun, which is a giant ball of superheated gas, the core of it is where nuclear fusion happens, which, as we just talked about, these nuclear reactions produce neutrinos. And so the core of the sun produces a ton of neutrinos, which come out and eventually come to Earth. The surface of the sun, which is where all the light comes from, is only telling us about, for the most part, what happens on the surface. You can learn some stuff about inside based on what you see on the surface, But the light coming from the sun that we see, that light is coming from the surface. But the neutrinos are coming from deep inside. So they tell us something about what is happening deep inside the sun. And when we realized this, we started looking for it. So a couple decades ago, the first attempt at doing this was called the Homestake experiment, which was a giant neutrino detector deep underground in a mine, the Homestake mine, in South Dakota. And the reason it has to be underground is because this detector is very, very sensitive, and lots of stuff that hits the detector might not be neutrinos. But that neutrinos can pass through the rock, whereas the other stuff, if you put enough rock in between you and between your detector and the source of that stuff, hopefully can't. So that's why neutrino detectors very often are deep underground.
Nathan.
But there was a problem. The problem was there weren't enough neutrinos. So I just showed you Homestake, which was kind of the first attempt, but there were other attempts, SAGE and GALEX and Kamiokande, for example, and they were all looking for a particular kind of neutrino, and they couldn't find it. They saw some of it, but not nearly enough of it. And that's what this plot is showing, is sort of each of these detectors didn't see nearly as much as we thought we'd see, given our understanding of nuclear physics at the time. And so the search was on to try and figure out what was going on. Maybe we were just not looking with the right detectors. Maybe we weren't looking hard enough. People were pretty confused, but people started looking really hard. So I'm showing two of the big experiments that eventually solved this mystery that we're looking. On the left, that's Super Kamiokande in a mine deep underneath the ground in Kamioka, Japan. And this thing is enormous. You can see that those people are in a dinghy floating on what looks like water. And then there's all those globes, right? Well, so those globes are parts of the detector, and so is the water. And when this thing is operational, that entire chamber is full. It's basically a gigantic underground lake. That thing on the right, which looks like, you know, the beryllium sphere from Galaxy Quest or something, is the detector in the Sudbury Neutrino Observatory in Sudbury, Ontario, which is deep underground in a copper mine. And these experiments and others discovered that what was happening is there were enough neutrinos coming out from the sun, but the previous experiments had only looked for one type. It turns out that the type that we expected to be produced by the sun. It turns out that in the time that it took for those neutrinos to leave the sun and reach us, they changed. The neutrinos can change between these types, electron neutrinos to muon neutrinos to tauon neutrinos, vice versa, back and forth. And we have some understanding of how this works and why, but we don't actually understand how to connect it to our understanding of particle physics. And this is a big mystery. And discovering this and explaining where the missing neutrinos from the sun were going won the 2015 Nobel Prize in Physics. So but that's the past of detectors. What are the new detectors that are coming out look like now? Well, the one I'm most excited about is IceCube. IceCube is in the South Pole. It is in fact very close to the real South Pole in Antarctica. And this is a photo of IceCube right under the aurora. But I've lied to you a little bit. This isn't IceCube. It's just the tip of IceCube. IceCube is it's called that because it's 1 cubic kilometer of ice. That thing I just showed you is the surface. It's a tiny piece at the top. In this diagram, you can see that the Eiffel Tower is put in for scale compared to just what IceCube actually is. So what you're seeing here is that in the Antarctic ice shelf, scientists drilled down a kilometer down beneath the ice and filled it with little detectors that are very sensitive and designed to react when a neutrino passes through. And by And by using enough of these detectors together, first off, you can get enough sensitivity to actually see your neutrinos. And second off, you can trace a path from where the neutrino came from. So you can tell what its source was, which is really hard. Most neutrino detectors can't do this. So now let's finally get to the fun space stuff. Let's talk about space. What are the other things other than the sun that neutrinos can be our X-rays for, that can tell us about what's going on inside these space things? So I'm going to go through a bunch of these. The first one is core-collapse supernova. When a star, like our sun, often much more massive, runs out of fuel that's powering the fusion in its core, it can no longer hold itself up. Stars are held up by the heat happening in the fusion at the center. When that heat goes away, the star collapses. Material falls in under its own gravity. At some point, the center of this star becomes really, really dense. So dense, in fact, that it starts to become one gigantic atomic nucleus, a thing called a neutron star. This is like something the mass of our sun, made of basically nothing but neutrons, and 10 kilometers in size. So incredibly, incredibly dense. This is something like a neutron star could basically fit on inside New York City or on Pajarito Peninsula. When it gets that incredibly dense, it becomes hard. And things now, instead of falling inward, they bounce off of it. And so the material that was falling into the star starts to bounce off of this giant atomic nucleus at its center. Then at some point, that bounce expands outward and causes the star to explode. That's the story. One big question about this that we didn't understand for a very, very long time is after stuff bounces off and causes the explosion, it doesn't always explode. In our simulations and in our models, it would sometimes just not. Stuff would bounce off, but eventually it would fall back in. It's like dropping a bouncy ball on your floor. The first time it bounces really, really high, but it doesn't fly off into space. It bounces again and again and eventually falls to the ground. So what exactly was powering this? Well, in 1987, we got a clue. In 1987, a star died close enough that we got a really good look. So what I'm showing you here on the left is a starscape. And this was not an optical camera, but it could have been. And you see that really, really bright point? That's the dying star. That's the supernova. And at the time, it was the brightest star in the sky. What I'm showing you on the right is the same star. Well, now it's not a star anymore. Way zoomed in. It's a Hubble telescope image of the remains of this star after it exploded. And you see that red ring? That is the shock wave expanding outward from the explosion. And this is a 2D image, right? We don't have the full 3D picture. Those sort of red arcs, those spiral things, are coming from the fact that we're looking at something that's actually in 3D from an angle. So that's an effect of our perspective. But when we saw this thing, it was so close that we got a lot of information. We saw it in light, we saw it in radio, gamma rays, we talked about those, and neutrinos. The Kamiokande detector, I think you remember that, I mentioned it, it detected neutrinos from this, as well as some other detectors. And what this told us was that neutrinos, it turns out, are what power the explosion. So after stuff bounces off the neutron star, when the neutron star is forming, that's a nuclear reaction, and it's producing a ton of neutrinos. Most of them fly off into space, never to be seen again. A couple of them reach us, and we detect them. But some of them get absorbed behind the bounce, so that you have the shock wave bouncing off your star, and some of this material gets absorbed in the star by this infalling material, and it heats it up. and then it expands. And it turns out that the heating from the neutrinos, we now know, is what causes these stars to explode. This wasn't the only thing that told us this. There's lots of other evidence, and there's still open questions. Core collapse supernovae are one of the biggest, hardest problems in astrophysics. But this story has now, the story I just told you is now the widely accepted idea for why these stars explode. It all comes down to these ghosts from space, these neutrinos. And a big hint for that was the detection in 1987A. Another place where neutrinos are incredibly important is something very close to my own heart. This is something I've studied a lot in recent years, is neutron star mergers. So you may remember hearing in 2017 about this event where all the gold, a Jupiter's massive gold, was produced. That was the neutron star merger. What happened is, after these are these cores of dead stars we just talked about. This is what's left over after a star dies, and it's basically this big atomic nucleus. And sometimes they hit each other. Two of these stars will collide. And when that happens, more nuclear reactions happen. And it's an incredibly violent event. We now know that these are what produce short gamma ray bursts, which are some of the brightest events in the universe, most energetic events. And they produce an afterglow called a kilonova, which we can see. And we did see in 2017. And when this happens, these nuclear reactions fuse and create heavy elements, things like iron, gold, silver, lead. These elements aren't produced naturally inside stars. They're produced in events like this. And we now believe that this is where most of the heavy elements in our universe, the heavy elements in us, come from. We contain the remnants in our bodies of neutron star mergers. And understanding how those nuclear reactions work and what happens, you really need to understand neutrinos. This is just eye candy from my own research on this topic. Another place where neutrinos show up in space are supermassive black holes. Almost every galaxy has a black hole at its center. What I'm showing you in this picture here is the galaxy Centaurus A. The brown stuff, that's the galactic plane. This is a galaxy much like our own. It's a spiral galaxy. The blue stuff, those arms reaching up and down off the plane, those are the jets of ultra-relativistic material being thrown out by the black hole at the center. And these black holes are huge. They're millions of times the mass of our sun. And these jets are enormous. You can see that these things are going way further out than the size of the galaxy itself. And lots of crazy stuff happens inside these jets, as you might imagine. Recently, in 2018, we detected both a neutrino and a gamma ray coming from what we now believe was a supermassive black hole at the center of a galaxy. The aptly named, very memorably named Blazar TXS 0506 plus 56 produced, there was an event where a lot of particle physics happened that produced, among many other things, a gamma ray and a neutrino. Probably lots of gamma rays and lots of neutrinos. And we detected a gamma ray in what's called the Fermi detector and in IceCube. Remember IceCube? IceCube detected the neutrino. Fermi is a satellite. It looks like this. And it can kind of localize where the gamma ray came from, much in the same way that the neutrino detector, IceCube, can kind of localize where the neutrino came from. And they both pointed at that blazar, which is what I'm showing here in this plot is basically that this is what happened. So both of these plots are kind of showing the same thing, left and right. They're two different detectors. But what you're seeing is, or they're two different measures of the same detection. The colors are where Fermi thinks the detection is, and the circles are where IceCube thinks the detection is. And they line up perfectly, and they happened at the same time, or close enough. The neutrinos don't quite travel at the speed of light, and so the neutrino got here a little later. But given that, they arrived in such a way that we believe they came from the same event in the same place in this supermassive black hole. And so neutrinos can tell us about what happens in these jets produced by these behemoths. So what's the future of neutrinos from space? Well, many times now, it's becoming routine. We've detected gravitational waves through the gravitational wave detectors that came online recently, such as LIGO and Virgo, that have detected the in-spiral merger of black holes and neutron stars and all sorts of amazing things. This is also going to happen eventually for something that produces neutrinos. So if we have another galactic supernova, one like the one in 1987, and we're due for one, we're not only going to see neutrinos, lots more neutrinos, because our detectors are way better now, and light, like we did the last time, we're also going to detect the gravitational waves, and we are going to see everything, and we are going to learn so much. The next galactic supernova, I think, is going to be really, really cool and really, really exciting. Another thing that is really exciting about the future of neutrino astrophysics is looking into the very distant past. So what I'm showing you here is a map of the leftover heat from the Big Bang. This is what's called the cosmic microwave background. And it's actually in a frequency that you can detect. If you turn on an old TV to no channel and you hear the static, some of that static is an echo from the very beginning of the universe. And it turns out that there should be something like the cosmic microwave background, but for neutrinos, called the cosmic neutrino background. It's very, very hard to detect, but people are trying. And if we ever do detect it, it will tell us some really interesting things about some mysteries that we believe are tied to neutrinos. Like, for example, it might tell us something about this question of how neutrinos fit into the rest of our understanding of particle physics. We understand a lot about that, but there's some missing stuff. It might also tell us something about dark matter. People have conjectured that that there might be a fourth kind of neutrino called the sterile neutrino, which might be what dark matter is. And it might tell us about antimatter. And in our current understanding of physics, there should be an equal amount of antimatter and matter in the universe. But fortunately for us, there isn't. We exist because there isn't any antimatter to come along and annihilate us. Why is that? Well, neutrinos are an excellent laboratory for trying to understand this because they have both matter and antimatter parts, and they're fairly easy to produce. And because there's the mysteries that I just mentioned, hope is that maybe all these mysteries are somehow connected. So that's where I think I'll leave you with these big open questions that I think are very exciting about neutrinos that we might be able to answer in the future. Now that I've told you about all the cool things that they can tell us basically as particle detectors, if we have a telescope, we can think of our neutrino detectors as telescopes or X-rays that let us look inside the things in space. So I think at this point, I will stop and take questions.
Okay, thank you, Jonah. That was a very nice presentation. We do have some questions. There was a couple of questions about Super Kamiokande. Can you explain that detector a little bit more? What is the purpose of the water? What are those globes on the wall and that sort of thing? How does the thing work?
Yeah, great. So let me go back to that picture. Somewhere in here. Yeah, here we go. So Super Kamiokande is a Cherenkov detector. So you may have heard of this thing called Cherenkov radiation. It's why, like, if you've seen pictures of nuclear reactors, there's like a blue glow. What's going on is that when particles travel through water very quickly, that can produce light, which we now call Cherenkov radiation. The way Super Kamiokande works is that it makes a really big space of water for particles to travel through very fast, particles like neutrinos. Technically, what happens is the neutrinos actually interact in some other way inside the water, like they hit an anti-neutrino particle or something. And when that happens, that reaction creates other particles which are moving very fast. And those particles, like electrons and something, for example, produce the Cherenkov radiation. Those globes on the walls of Super-Kamiokande, which look kind of like fish eyes, each of those is a photodetector. It's essentially an extremely sensitive camera that waits for the glow of the Cherenkov radiation and then takes a picture of it. And that tells us we saw a neutrino.
Okay, yeah, that I think that probably answers the questions. There was another one relative to types of neutrino detectors, and so Super Kamiokande uses water. Sudbury also uses water, correct?
Sudbury, I'm trying to remember what SNO uses. I do not think it's water. I think it's it might be gallium, like the SAGE and GALEX detectors. I don't remember, but it's not water.
So then the other question is why do gallium and chlorine make good neutrino detectors? Are they detecting different flavors of neutrinos than water does, or how do they work?
Yeah, great question. So yes, they detect different flavors of neutrinos. And one sort of key in these big detectors is basically what you're trying to do is you're trying to detect you basically almost never detect the neutrino itself. You basically always detect what happens when the neutrino hits something else and makes another particle. And these various different kinds of detectors are good at detecting different kinds of particles that are produced when a neutrino hits something else. So water detectors are really good at detecting Cherenkov radiation. This is actually how IceCube works too. Except the water is ice. And that's good for detecting charged particles that move very quickly through water. The other detectors detect other kinds of particles that interact with them. So sometimes light, the gallium detectors, I believe, use light, although I could be wrong about that. I do not know how the chlorine detectors work. I don't remember.
Okay, we have a couple of comments saying that Sudbury actually uses heavy water, D2O.
Oh, okay.
Yeah.
Thank you for the correction.
Right. How do jets from supermassive black holes produce neutrinos?
Yeah, let's go look at this picture because it's very complicated. Here we go. So it has to do with the motion of charged particles. If you have like a proton or an electron moving very quickly through the jet, it will sometimes hit other stuff. This is always how it works, by the way. Stuff hits other stuff. And when it does, you can get a cascade of subatomic particles, including photons. Photons are light particles, and that includes gamma rays. And also things like pions, which we didn't talk about, and electrons, and I mentioned muons. And a muon neutrino is what we saw in IceCube. We don't know, I don't know, maybe someone who knows more about this could comment, or maybe it's certainly detailed in the IceCube analysis. I don't know whether it was always a muon neutrino, but when muons are produced in these sort of jet interactions, so are neutrinos. So it's not a nuclear reaction in the way that I talked about for like supernovae. It's more like what happens in a particle accelerator, like the LHC. Basically, this jet can act as a gigantic particle accelerator. It has huge magnetic fields, and those magnetic fields can accelerate things like protons and electrons to extremely high speeds. And then when you hit stuff at high speed, when you have two particles going really, really fast, very close to the speed of light, and they collide, they produce more particles. Basically, it's actually Einstein's equation, mc squared, but in reverse. You have a lot of energy, and it produces mass.
So the jets are like enormous particle accelerators, and they produce a whole slew of subatomic particles, and some of them are neutrinos.
Exactly. Yes.
Right. Mm-hmm. Yeah. Okay. Here's a question that I'm sure you'll be able to answer. When is the next supernova supposed to be?
Now. We're supposed to get about 2 every century, and we're due. in the galactic supernova. There's actually supernovae happening pretty much all the time. We see them, but they're too far away to get neutrinos from them. But basically every day there's a neutrino detected by, or a supernova detected by a telescope, because we can see really far away, and there's 2 per galaxy, and we can see a lot per 100 years, but we can see an awful lot of galaxies with a telescope. And supernovae are really, really bright.
So I guess that leads to a follow-on. Is there any way, since neutrinos are an X-ray machine for stars, is there any way we can use neutrinos to predict a supernova?
Yes. This is actually an active area of research. People work really hard on this, including some Wendell scientists. For example, there's a scientist who I collaborate with here at Wendell named Wendell, who studies exactly this. When the star is near the end of its life, but before it actually dies, the neutrinos that are being emitted in the core, where it's doing all this fusion, like our star produces neutrinos, the luminosity of those, meaning the number of neutrinos, goes way up, and in a specific way. So if we can detect that, we can know when a star is going to explode, and we can point our telescopes at it, which would be amazing. We'd get to see the very moments when the star dies.
That would be cool. Do we have enough neutrino detectors working to do this right now?
If we're really lucky, but more are coming online. So the Dune neutrino detector would help a lot. That's sort of a next generation detector. That's kind of an extension. I don't know. I actually don't know how it works, but it's an American detector.
Okay. Another question: how fast do neutrinos move?
So this is a really, really interesting question, and the answer is we only kind of know. So neutrinos move almost the speed of light, but not quite. So in the 1987 A detection, much like the Blazar detection, the neutrinos came later than the light. You shouldn't expect them to come earlier, because nothing can travel faster than light. But the fact that they came a little later means that they don't travel exactly at the speed of light. They travel a little bit slower. And the speed at which they travel depends on their mass. And we don't know what the mass of the neutrino actually is. It's really tiny and not 0, but it's so small that we haven't quite pinned it down. And this is actually this is tightly related to other questions about neutrinos. For example, the neutrino mass is tightly related to how neutrinos oscillate. That's fairly complicated, so I don't want to get into it, but neutrino oscillations depend on the neutrino mass in a way that we don't fully have a handle on, because we don't know what the mass is.
But for so I'll elaborate a little bit on that question, which wasn't mine. If neutrinos traveled at the speed of light, you'd actually see them before the light, right?
Yes, you would, because they come out earlier.
Right.
That's true.
Yeah. So the fact that we saw them later, we can't really deduce the speed from that delay, because it had to travel through the star first.
Yes, that's right.
Right. Mm-hmm.
Good correction. Thank you.
Yeah. Yeah, there's more questions coming in all the time. Could you put an upper bound on the energy of formation of the muon in the jet to constrain the muon mass? Maybe this is too obscure a question. That's from Joyce Guzik, so maybe you can argue it out with her at some point. But
yeah, we should talk, Joyce. I don't know the answer. I'd have to think about it. But let's talk later.
Okay. What fraction of the mass in the universe is neutrinos?
Yeah, that's a great question. It depends. It depends on the age of the universe. So currently, probably not a lot. Most of the mass in the universe is baryons. Well, most of the luminous mass, something like 25% of the mass in the universe is what's called baryons, which is stuff, but not neutrinos. It's things like protons and neutrons. But in the end, the rest of it is stuff we don't know, dark matter or dark energy. So if the stereoneutrino is dark matter, then about Oh, sorry, I got that wrong. 5% of the universe's mass is stuff, baryons. 20% is dark matter, 70% is dark energy. So if sterile neutrinos are in fact what dark matter is, then about 20% of the universe's energy content would be neutrinos, 4 times as much as like normal stuff like us. If it turns out dark matter is something else, then probably the amount of mass that in the universe that is currently neutrinos is very small. But in the distant past, right, I mentioned there was this cosmic neutrino background, right? There was a point in the history of the universe when pretty much everything was a neutrino, just a few moments after the Big Bang.
Right. Okay, here's another one. How can you tell the difference among the different neutrinos? How do you know which one you're detecting?
Yeah, this is a really good question, which I actually don't have a good answer to, other than it's really complicated. So the people who study this figure out very carefully when I mentioned that basically the way all these work is that a neutrino hits something else and then you detect what's produced by that collision. People very carefully work out what is produced by every possible collision of every possible thing with the different kinds of neutrinos, and then they very carefully work out what the signature of that is in their detector. It's hard, but people have gotten pretty good at it.
And here's a kind of a complicated question that actually may be two different questions. First, could you talk a bit more about what happens when neutrinos from space pass through us?
Yeah, for the most part, nothing. They pass through us harmlessly because they don't interact with our bodies. And if they did interact, that's a very small, like a single neutrino colliding with us. I mean, it takes that giant detector to detect that kind of thing. So we're safe.
But it must happen occasionally, right?
It must happen occasionally. I haven't thought about what that rate must be. That'd be interesting to work out. But this kind of thing is, for the most part, harmless. Like you're being irradiated every moment by all sorts of radiation coming from the sun, right? Like we get alpha, beta, and gamma particles coming from the sun when we go in an airplane, or from bananas, which contain a radioactive isotope of potassium. And it's really only dangerous in sufficiently high dosages. Neutrinos basically do nothing to us.
Okay, and then she asks, you talked a bit about elements, materials that originated elsewhere making their way to our bodies. And I think what she's referring to is
the neutron star merger
elements in stars, and how do our bodies incorporate those elements?
Yeah. So what I meant by that is that our bodies contain some trace amounts of heavy elements, right? Like we actually need things like gold and some heavy metals to survive, right? It's a little bit, this is kind of what vitamins give us. The way that they got into us is that they're on Earth. And the way that they got on Earth is pretty interesting. We may have only had all of the stuff that is in us, all of these elements may have only come from one neutron star merger event, which happened in the Milky Way. These events are very, very rare. And we know this because some galaxies don't have these heavy elements. It seems like it's not like every galaxy that we look at of the same age has the same amount of stuff in it. It depends on the galaxy. There's some factor of chance. And neutron star mergers produce enough of this stuff that it can basically feed a whole galaxy. So what happens is a neutron star merger happens. This is a huge explosion. These heavy elements, stuff like gold, are produced. And it's thrown out in a big expanding cloud of material. Over time, a long time, the forces in our galaxy move that cloud of material around. Stellar winds push it. The jets from supermassive black holes push it. It gets pulled by the gravity of stars. And at some point, it gets pulled into what is not yet, some of it gets pulled into what is not yet our own star. And as our star and our solar system form together, some of this material is pulled into it. And so the heavy elements that are in us most likely came from a neutron star merger that happened long before our sun was born, and then became part of both the sun and us in that formation.
Yeah, I think that probably answers the question. What have neutrinos told us about our own sun?
Yeah, great. So there's a very complicated nuclear reaction that happens in our sun that produces the heat that we enjoy. And it has several stages as it sort of merges different elements into heavier and heavier elements, which eventually stop with iron. And the neutrinos that are produced by the sun tell us exactly how much of those reactions are happening in each of these stages. Not exactly, but they tell us about that. And they tell us more if we didn't have to account for the fact that neutrino oscillations happen. And so that kind of muddles it up a little bit. But that chain of reactions, which was actually predicted before we detected neutrinos, when we finally knew that all the neutrinos, when we finally filled up the deficit and saw all the neutrinos we should from the sun, that told us that those reactions in the sun that we predicted are happening. And that actually confirmed our understanding of how stars work, that they're powered by nuclear fusion.
Yeah, excellent. See, are neutron star mergers going to become more or less frequent?
Oh, that's an interesting question. More with time. So basically there's a cutoff. Well, more until less. At some point, the universe is going to, the way the universe currently looks is going to end, and things are going to be torn apart by dark energy, and there's going to be nothing left. But until then, more, because neutron star mergers are powered by neutron stars, and those are the cores of dead stars. And so it takes time from the beginning of the universe for stars to form, then die and form neutron stars, and then for their orbits, usually stars are born in binaries, to decay until they collide. And so there's a cutoff. There couldn't have been any neutron stars up to a point when the universe was old enough for them to exist. And then a little later until there was the point where neutron star mergers could happen. Now we're getting more and more stars, and more of the stars that have been born are dying. And so over time, we'll get more and more of these events. But this is on a really, really long time scale, much longer than a human life. But let me answer another part of that question, which is, will we see more and more neutron star mergers? And the answer to that is also yes, because our detectors are getting better. So at some point in the distant future, which I hope to be alive for, I think it's going to be not that long, there should be detections of neutron star mergers should be totally routine. We should be seeing them like every day, just like we are for supernovae, once we get good enough detectors.
That's great, thank you. Okay, so the person who asked about the elements making their way to our body asks, are heavy elements more likely to be created through neutron star mergers or through a slowly accumulating process of neutron capture?
Great. Yeah, so we now believe it has to be neutron star mergers for the heaviest of elements. But you're right, whoever asked that there are other processes. So there's something, I think what you're referring to, the neutron star merger process is what's called the R process, or rapid neutron capture. And there's a slower version of this called the S process, for slow neutron capture. And there's even something called the I process, which is somewhere in between. The S process and the I process are believed to actually happen in very massive stars. But the abundances are too low to explain the heavy elements that we see in the universe. So the R process seems to be it for at least producing enough of the heavy elements that we observe.
Good. How many neutrinos are emitted in a U-235 fission?
Oh gosh, I don't know. I'd have to actually look at the reactions. I don't know that off the top of my head.
And what is their energy distribution? Oh well, okay. Okay, I think we've reached the end of the list of questions. I don't see any. Have we missed anything? Yeah, no, I think that's all. Okay, it's 10 minutes to 8. If there aren't any more questions, we can say good night. I hope you all enjoyed this presentation. I certainly did. I think Jonah did a great job. Thank you very much, Jonah, for sharing sharing this information with us. And we look forward to future talks in the PEEC astronomy series. These talks happen every Friday evening at this time, and the next one will be on the 28th of August, a week from tonight, given by Joyce Guzik on observing variable stars from space. So that should also be very interesting. And then at the beginning of September, in the first Friday of September, we'll have our regular talk talking about what's up in the night sky in September. And we have several people who just chimed in saying, thank you, Jonah, very enjoyable talk. Just convey that to you, and thanks to everyone who has joined us for this.
Yeah, thanks a lot, everyone. This was a lot of fun. Hope to see you next time.
Yep. Okay, good night, everyone.